Everybody's ready? All right.
Hello and welcome to NOAA's National Ocean Service Science Seminar Series. My name is Tracy Gill and I'm the coordinator for this seminar. Today is the second seminar in a special seminar series, and you'll hear more about that after a few logistics. Since we have 4 lightning talks today, people in the room, please hold your questions until after all speakers have finished. And folks online, you can go ahead and type your questions into the chat, but we will not get to them until after all speakers have presented. If you are interested in getting a PDF copy or MP4 recording of today's presentation, please contact any of the people that you see online, Emma Kelly, Gina DiGiantonio, Laura Newcomb, or myself, Tracy Gill. And if you are not on NOAA's weekly science seminar list but you'd like to be, contact me and I will add you to the list. Folks in the room, please silence your phones and sign in. And now I will turn the floor over to Emma Kelly, a contractor with CollaboraLink supporting the NOAA Research Council. And Emma will introduce the seminar series, hosts, and speakers and seminars. Take it away, Emma.
All right, great. Thanks very much, Tracy. All right, so welcome to this webinar on sustainable use and stewardship of ocean and coastal resources, the second of 4 seminars in the inaugural NOAA Science Report Seminar Series. The sponsors for this seminar series include the NOAA Research and Development Enterprise Committee, Gina DiGiantonio, Laura Newcomb, myself, and of course, the One NOAA Science Seminar Coordinator, Tracy Gill. The NOAA Science Report is an annual report that highlights NOAA's scientific accomplishments for the year. The NOAA Science Report celebrates NOAA's research and development in 4 sections: an introduction, science highlights, bibliometrics, and a final section on NOAA's scientific workforce. Together, these sections highlight how NOAA's research products impact the lives of all Americans. The 2019 Science Report will be released later this month on the NOAA Research Council website, so stay tuned for that. This 2019 report spans the entire range of NOAA's mission, and there are 64 science highlights featured in the 2019 Science Report. Today, we welcome 4 speakers whose work is featured in the Science Highlights section on sustainable use and stewardship of ocean and coastal resources. Our speakers are Melissa Karp, who received her MS in Marine Science from the College of William & Mary School of Marine Science at the Virginia Institute of Marine Science in 2015, and her BS in Biology and Environmental Science from Tufts University in 2013. Currently, Melissa is a contractor with ECS Tech, working on behalf of NOAA Fisheries Office of Science and Technology. Her work focuses on supporting efforts to advance stock assessment methodology in the U.S., particularly related to the incorporation of ecosystem and climate information in the assessment process. Dr. Gary Wikfors' terminal degree is in phycology, the study of algae, but he has always worked at the intersection of phytoplankton and the bivalve mollusks, such as oysters, clams, scallops, and mussels, that derive their nutrition from phytoplankton. As chief of the aquaculture sustainability branch, Gary has a hands-on role in several current team initiatives. 1, nutrient bioextraction using shellfish aquaculture. 2, probiotic bacteria for use in shellfish hatcheries. And 3, shellfish cellular immune response to environmental variation. Dr. Rick Stumpf received a BA degree in environmental sciences from the University of Virginia and MS and PhD degrees in marine sciences from the University of Delaware. Dr. Stumpf developed methods to use satellite data and modeling to understand coastal eutrophication, habitat change, and algal bloom monitoring and forecasting. He leads NOAA's efforts to translate forecasts of harmful algal blooms from research to operation. And lastly, we have Dr. Alexander Gilerson, who received his BS, MS, and PhD degrees in engineering from the Technical University in Kazan, Russia. Since 2003, he has worked at the City College of the City University of New York in the Optical Remote Sensing Laboratory as a senior scientist and then as a professor. His current research interests include the development of advanced algorithms for the retrieval of properties of ocean particulates, detection and monitoring of algal blooms, hyperspectral polarimetric imaging of the ocean body, and validation of ocean color satellite sensors. So each of these 4 speakers will have about a 10-minute presentation, and then we will have a question and answer session at the end. So at this point, I'm going to hand it over to Melissa.
All right, thank you, Emma, for that introduction. So I'm going to be presenting on the results of a workshop or working group looking at how we can improve our capacity to deal with shifting distributions and changing scarcity. So we're all aware that oceans are changing from increasing frequency of marine heat waves, increasing ocean temperature, and decreases in pH. And we're already seeing some of the impacts of these changes on the marine communities and marine fisheries, such as shifting species distribution, changing productivity, changing species interactions. For instance, an example of that is shown in the maps here, where you can see the northward expansion of black sea bass as a result of increasing ocean temperature. And these are having impacts on fisheries management. It can affect our surveys and staff assessments, estimates of spawning biomass, maximum single yield, and biological reference points, as well as the effectiveness of spatial and temporal management measures. It can also lead to issues with quota allocation, particularly as species shift across jurisdictional boundaries. So this leads us to then ask, how do we best position ourselves to address these growing challenges? And to help answer that question, we put together a working group to charge with developing specific actionable recommendations to better incorporate environmental and climate information into the fisheries management process. And we were specifically looking at two main issues, the shifting species distributions and changing stock and ecosystem productivity. The work group was comprised of representatives from each of the science centers. We also have members from regional offices, Office of Science and Technology, and the Office of Sustainable Fisheries. So the work group identified 6 key components or areas of kind of the science kind of climate-ready management system where we felt improved capacity would better enable us to account for shifting distributions and changing productivity. And these 6 components are indicated in this kind of bullseye diagram here in the teal ring. And these include our ability to detect changes, so understanding what is changing, understanding why it's changing, so understanding the mechanisms of change, looking at what is vulnerable to change, so being able to evaluate risks and then prioritize the species accordingly, conducting assessments and forecasts, so looking at how will things change, trying to answer questions of how do we better deliver and use this information in our management advice, and then lastly, how do we prepare and respond to changes. And I'm going to walk through some of the key recommendations that this work group came up with for how we can improve our capacity under each of these key components. So the first component is the ability to detect changes. So the capacity of any fisheries management body to really effectively address species distribution shifts and changing productivity and develop a response strategy really begins with our ability to determine that a change has occurred, is occurring, or will occur in the future. And we noted that our kind of current capacity to do so is somewhat limited due to the kind of static nature of our surveys. And we felt that we really need to adapt to some changing data needs to really be able to differentiate between changes in abundance versus a shift in distribution or change in productivity. I'm just going to highlight a few recommendations we had to help us do that. The first was the need to expand or look at ways to expand the spatial and temporal coverage of surveys. So this could involve facilitating survey flexibility to track changes in species distribution, engaging and leveraging the capacity of fishermen and other stakeholders who are on the water, sampling fish maybe in different areas or times than our traditional surveys. Using integrated ocean observing systems and other advanced sampling technologies to provide some broader scale oceanographic information. Really coordinating research and survey efforts across adjacent jurisdictions, and tracking and monitoring indicators that can serve as early warnings of change. So looking at changes in catch composition, size of each, temperature, pH that can indicate that something is going on in the system. Not only is it important to determine that a change has occurred, but it's also important to understand what could be causing those changes. Understanding the underlying mechanisms of changes may improve our ability to predict and forecast those changes. So to help us to do so, we recommended collecting oceanographic habitat and multi-species information in all of our standard surveys. So you could compare, kind of relate the changes you're observing in the biological community, so there's changes in catches and survey abundance indices with your underlying environmental conditions. Additionally, looking to evaluate how stock availability to survey and fishing gear can change or is changing with changing environmental conditions, as important as changes in catchability can impact the estimates of abundance from surveys. Lastly, just conducting more process-oriented research that can go into improving our modeling and assessments, so looking at how temperature and ocean acidification affects important vital rates like mortality and growth. We did recognize, however, that not all species and ecosystems are vulnerable or equally vulnerable to changing conditions, and not all changes may warrant a response by management. So a key component in this process is to evaluate the magnitude and relative importance of distribution shifts and changes in productivity, so using spatial analysis techniques or sensitivity analysis to help do so. Also running vulnerability assessments and tiered risk assessments. I kind of pulled some figures from the recent Northeast vulnerability assessment, and using that information to help prioritize the species at most risk resulting from changing ocean conditions. And then you get into the assessment and the forecasting phase, and generally, consideration of ecosystem information directly in the stock assessment is not as explicit as it could be. So our recommendations really formalize the consideration of ecosystem dynamics in the stock assessment. We recommend including this as part of the kind of standard terms of reference in each stock assessment process. Also capitalizing on advancements in spatial, temporal, physical, ecosystem economic models that have been developed in a couple of regions. Evaluating model diagnostics and predictive skill of forecasts, so looking at how models which included environmental information or covariates compare to models which did not include those covariates, and then presenting that information to managers. We also recommend exploring the use of ensemble models and multi-model inferences, as this can enable a more full evaluation of the alternative states of nature, as well as a more full characterization of some of the uncertainty that might be in the system. So to facilitate kind of climate-informed decision-making that's able to respond to a dynamic and changing environment, that information needs to be communicated to managers effectively and efficiently to ensure that they are left with a clear understanding of when and how information can and should be used in making decisions. So to help with this, we recommend establishing more routine reporting and standardized templates to help report this information on ecosystem dynamics, species distributions, and productivity in a more standardized format. I pulled an example here, two-page summaries called APEX, which are being developed in the Alaska region, as an example of what a standardized template could look like. Also recommend utilizing and including decision support tools in stock assessment reports, so using decision tables and decision trees to help communicate risk and trade-offs. It's also really important to facilitate more regular engagement between the scientists and managers through regular open dialogue at workshops and debriefs. And that brings us to the last component of the kind of the management side, the management actions, and just a few recommendations on what kind of managers should be looking to do in the future. So we discussed the need for managers to plan for future scenarios, so to use management strategy evaluations or structured scenario planning, and to develop those plans with adjacent jurisdictions. I also mentioned at the beginning that one of the impacts of shifting distributions is that it can lead to lessen the effectiveness of spatial and temporal management measures. So it's important that managers reevaluate their spatial temporal management and consider using more dynamic ocean management practices. Lastly, we recommend looking at ways to develop more responsive harvest controls. So in the end, it was clear that traditional methods and assumptions may need to change to better account for changing distributions of species and changing productivity. Recommend on the management side that they explore future areas, reevaluate spatial temporal management procedures, and develop more responsive harvest control rules. There also really needs to be improved collaboration and communication between the scientists and the managers to help increase the flow and use of this information in the stock assessment process. And that we still need to improve our capabilities in terms of our ability to detect changes, understand the mechanisms, forecasting future changes, and then using that to help evaluate best management strategies, and respond to those changes. And that's all I have.
Thank you.
All right. Thank you very much, Melissa. So next we're going to turn over to Gary for his presentation. Gary?
Yes, I am here, and I want to first say thank you to Emma and Tracy for organizing. I want to express gratitude for being included in this series. And I'll start by kind of deflecting a lot of the credit for this work. On the cover slide here is a photo of Darien Mizuta, who just finished a 3-year National Research Council postdoctoral fellowship in our laboratory. It was funded by the Fisheries Office of Aquaculture, so thanks to them for that support. And all of the skill and most of the work that I'll be presenting is attributable mainly to Darien, who was a very effective young scientist. In my defense of my role, I'll say that the opportunity for this work, and I'm happy to be speaking about an opportunity, not about a threat or a vulnerability today. The opportunity came from a market analysis of what shellfish are imported. And so the other figure on the cover slide here is the Northeast U.S. region imported shellfish. And the red bar is mussels. And as you can see, for the first half of the last decade, at least, and it's continuing, mussels are the most imported shellfish in our region. So we thought this was an opportunity to that maybe we could address in some research. Now, I'm going to ask a weird question for a webinar. How many people have had eaten blue mussels from Prince Edward Island? Raise your hand. I'm picturing hands going up in cubicles and offices all around the agency. But so the Prince Edward Island mussel aquaculture industry has kind of done a great service for us in getting Americans accustomed to eating blue mussels, which previous to about 2000 was a very small niche ethnic market in the U.S. And now you can find blue mussels in restaurants everywhere. And I can go to my local supermarket and buy 2 pounds of mussels for $7 or $8. So it's really become a very new kind of seafood that we're eating. And I visited a number of years ago Prince Edward Island and saw what their cultivation practice looks like. It's the same as the way mussels are grown in other parts of the world. New Zealand, a lot of countries in Western Europe, and until recently in California, there have been commercial mussel farms, either inshore or offshore, that look like the diagram I have in the upper right of this slide, where there's a series of anchors and floats that hold a horizontal long line from which are suspended what are called droppers, and these are either rope or socks made out of plastic mesh that hold the mussels. And the mussels are eating natural plankton in the water, and so it's not a fed aquaculture. It's considered to be a very sustainable kind of seafood production. Now, the question that Darien and we addressed to begin with is there an opportunity in our region off the southern New England shelf for a new blue mussel aquaculture industry? And we borrowed a concept that's used in fisheries science but isn't often applied in aquaculture, and that's a habitat suitability assessment. And Darien is an oceanographer and is very adept using data and reanalyzing and developing products from existing data. But we also collected some new information ourselves in the course of this work. But the idea was, if there was a suitable habitat in the southern New England shelf for blue mussel aquaculture, the additional barriers, such as competing uses of the space, would be worth investigating. So very quickly on the methodology, Diane took advantage of NOAA's monitoring database, which is, as I say here, a rich source of environmental knowledge that, unless it's used, or when it's used, gains value every time it's used. And this was publicly available data, local data of ours. What Diane did was, I think, a great innovation. She mapped the southern New England shelf in 3 dimensions. And latitude and longitude, it's fairly common to do, but she did the 3rd dimension of depth because, as you may recall from that diagram, the long line is suspended underwater, not at the surface. And the 2 environmental variables that we determined to be important were temperature and chlorophyll, which is an indicator in, especially offshore, of microalgae, phytoplankton, and that's the main source for food for mussels in that environment. Having done the mapping, we then tested our assumptions about habitat suitability by actually measuring mussel feeding, assimilation rates of phytoplankton on a site 7 miles offshore Cape Ann, Massachusetts, where Plymouth State University has a experimental mussel farm. And I'll show you some data from that. And then we started to identify what those other barriers might be, because we were getting some very positive results from our habitat suitability assessment. We did address harmful algal bloom biotoxins, and there's a couple of talks after this that I'm looking forward to very much, because this will integrate very well in offshore mussel aquaculture development. And then protected species, which is the great big topic that we are anticipating having to put some effort into. But I'll just give a little shout out for the method of how do you measure mussel feeding 7 miles offshore. I invite you to look at the paper below, which is a kind of innovative approach to communicating methods. It's a video type journal. All right, so the findings were very exciting. If I could, in one sentence tell you what we discovered, is that there's no bad place for mussel aquaculture off the coast of southern New England. If you get the depth right and at different seasons, and on the upper right of this slide you can see a number of plots, depth profiles of chlorophyll, and the depth of a good temperature range, which we determined to be between 5 and 10 degrees Celsius. That depth very often corresponds just below that with the maximum abundance of food for mussels. So it's a very, very good environmental situation. The best sites are a bit deeper to the south in the summertime, and a bit shallower to the north, but you can always find a good depth at every site. This is great news because competing uses becomes much less of an issue. Aquaculture very often gets relegated to the last place, the worst place that nobody else wants. In this case, we'll take it, and happily. The other finding is that this assessment strategy, this first doing using monitoring data to identify suitable habitat for shellfish aquaculture, and then field testing your assumptions with the candidate organism, is a transportable one wherever there's good data. And I'd invite you to check out the Coastal Aquaculture Planning Portal, which is a product from James Morris and colleagues in NCOS. A lot of great data available up and down all coasts of the U.S. that can be used in this kind of habitat suitability assessment for offshore aquaculture. And then the methods that we've developed and have demonstrated here for field testing with candidate organisms is now being used by our group to assess the potential for sea scallop aquaculture in coastal Maine. I'm getting a little short on time, so I'm just going to tell you that we did again, a literature-based study of harmful algal bloom pressures offshore, and that didn't seem to be any worse than nearshore situations, so that should be possible to manage. And then, again, a main finding here is that it's worth the effort to now address some of the remaining barriers, especially the protected species ones. And, again, very quickly, this kind of reiterates what I just said. We have a paper coming out in Fisheries magazine very soon that is titled Blue Mussel Farming Offshore is an Opportunity Good to Ignore. Our findings are drawing attention of both industry and the regulatory community in terms of addressing that last barrier of protected species. This approach of coupling performance measures with environmental data analysis appears to be transportable for other potential opportunities for shellfish aquaculture. And again, our example is working with sea scallops in Maine nowadays. And I'd like to finish by inviting you to look at our papers if you want more details on this. And again, thank you for your attention.
Thank you very much, Gary. All right, next we're going to hand it over to Rick.
Hi, thank you, Emma. Tracy. Okay, we're going to go down the coast to Florida here and talk about harmful algal blooms in Florida. For context, 2018 was one of the more severe blooms that Florida's experienced, about the 5th longest in time. An example of what the water would normally look like is on the left. The same beach during the middle of that red tide. You can see red tides are not really red, they're more brownish. What did the same beach look like when the bloom was going on? This is extreme concentrations, I should say, dramatic now. The organism is Cornea brevis, and key problem, it produces a set of toxins called brevetoxins. And these brevetoxins end out, unlike just about all other havotoxins, these can become particles in the air, become an aerosol. A mask will actually filter them out. Masks have been in the news a lot recently, but a surgical mask will actually work for these, unlike for viruses. And it causes a respiratory irritation. That means runny nose, coughing. First symptom most likely people get is they start coughing. But a runny nose, watery eyes, and so on. My experience is if there's one going on, I walk out on the beach, I feel like I've just come down with a cold. Leave the beach, I'm fine. If you're an asthmatic, however, or you have some other chronic pulmonary disease, it's a different matter. Asthmatics is a hazard, and there's in fact this Sarasota County experiences 54% increase in ER admissions for respiratory effects, and that includes pneumonia and other similar things. And there ends up being an economic impact. People go out to the beach, they're miserable, they hear there's red tide, and they decide at that point, anytime they hear the word red tide, they're going to just stay away from the beach. And so one study was up in the Panhandle. This was over 10 years ago at $6 million per month per county. If you go in more densely populated counties more recently, that economic impact can go up quite a bit. So a huge issue with this is if we know where the blooms are and where they might be, we can reduce risk. People have the perception that red tide, when it occurs, is everywhere all the time. This is partly done from the media because it's very sensationalized. The blooms are in fact quite patchy, and very important with the respiratory effect, it depends very much which way the wind's blowing. Offshore wind, you'll less likely to have respiratory impact. Onshore wind, you will have one. By the way, there's a lifeguard worker there wearing a mask during a red tide, and there's an anemometer happens to be right behind him on the board. So we know something about them. So there's some new approaches being used to find the blooms both before they come on shore to try to predict when they may show up and do a better job of detecting them. And there's a whole lot more technology we're working on that maybe would be appropriate for another one of these sessions, but I'll just touch on these. One method is underwater gliders. These are kind of looks like a yellow torpedo with wings, and they run on literally ballast. So they have they're neutrally buoyant. They pump in water, they sink, so they glide forward. The water is then pumped out, and they glide up and forward again. They go about 1 or 2 miles an hour, a couple of kilometers an hour, and so it's possible to monitor. They have a suite of instruments that includes temperature, salinity, depth, chlorophyll, and then every time they surface, they report back by satellite, cell phone, or some other method. There are models, new models, of course, three-dimensional circulation models to use. And then satellites. There are some new satellites. The Sentinel-3A, 3B is a particular one that the European Space Agency had put up, which has higher resolution, more wavelengths than the available satellites. Order of magnitude better resolution than what was available just a few years ago. So I'll just show some example data from some of these. And the Karenia itself, the organism swims up and down in the water. It swims up to light and typically swims down to nutrients. So the most nutrients on the Florida shelf are near the bottom. And the bottom is pretty shallow. And in fact, it's generally relatively clear. So you'll often have all the algae typically is more common near the bottom than near the surface. So what you see is an example of the glider on the side. This is one of the USF gliders. And there's a number operating in around the Gulf of Mexico. And it had a chlorophyll sensor which detects the fluorescence of chlorophyll. Now, all algae produces chlorophyll, and so detecting chlorophyll is not an indicator of Karenia specifically, but it's the potential of it. What you see is a trace. This is over time, which comes out as sort of distance, and you can see there's high chlorophyll near the bottom. At one point on this trace, there were cells identified. And they were at around 10,000 cells, a bit lower than the amount of chlorophyll, but you can see that most of the chlorophyll is near the bottom. So this is a potential indicator of where Karenia might have been. You can see a red patch on the left side of the graph, which is, I don't know if this thing works, but which indicates high chlorophyll. So it's possible with that information, that can be put together with models, and this is an example from that particular study. So a 3D circulation model, and if you put in the glider track, which you see the dates, 8/25, that's August 25th, where the glider was, you can see how far it moved from August 1st, August 31st, then to September 13th, and it was going, half degree of latitude is 30 nautical miles, about 33, 34 miles, 50 kilometers, and you can see that it moves about 10 kilometers a day. And so taking the model, you can actually use this as an input, say where a subsurface bloom might make landfall. So it's a possibility of, if we identify a bloom offshore, where it might actually show up at time. Now this was in 2018 when a very severe bloom occurred in Florida, so any offshore signal was actually totally overwhelmed by the intense bloom that was already going on the Florida shelf, but at least gives a demonstration of the potential combination. So with satellite data, we're actually working in a similar way. Karenia, because it does swim up to light in the daytime, once you have a dense bloom, they're typically visible. You might think of it swims up and waits with the satellite, which would be a way to look at it. And the new satellites measure a number of wavelengths, and we can also detect chlorophyll fluorescence quite well with this. And again, much better resolution and less noise than the previous sensor, which was the MODA sensor on NASA's Terra Nova satellites, which are now 20 and 17 years old, which is remarkable. They're still operating, but they are older technology overall. So Karenia blooms are most likely on the Florida coast in the summer. So if we see strong chlorophyll fluorescence signatures in that summer, fall, they're most likely to be Karenia over any other feature. So just to get a context, this is in the 2018 bloom. The current state monitoring program, each of these is a week's worth of data, so the week up to July 19th and the week up to September 20th. And this is extraordinary amount of effort. These are all counted by hand, through microscope. It takes about 20 to 30 minutes per sample, and they have to get to the right people. So you sit down and look at a week's worth of work. This is extraordinary amount of effort. Now, what I'll show next are satellite images from the one day during the week and how much more information we can get, or how much complementary information we can get overall. So we're looking on July 17th during the 1 week, and you'll notice the small area of bloom both near shore, near Venice, and it was not present north and south, just like the state. And then not only is it widespread, but how far offshore it had extended by the time we got into September. This covered about 150 kilometers, 150 miles actually, from south of Naples up to St. Petersburg, Clearwater at this time, and extensive bloom. So it's possible to actually monitor over time the development of these blooms. And so this is a huge job. We can't do anything if we don't know where the blooms are. So in order to get to the reservoir, in order to plan, we can now identify where the blooms are offshore, where they're likely to be, and this can actually set up other approaches in order to assess some impact and modeling. One of the next steps is in actually reducing respiratory irritation. We're working on a beach monitoring system, which is called the HABSCO, and which involves combining an iPod and a microscope and artificial intelligence facial recognition, which can involve volunteers, and so that's the trailer for a talk I'll do sometime in the future. And then we're also just now starting using small aerial systems, drones people might call it, to actually get right to the beach. The satellite's 300-meter data, which means we can't see within 300 meters of the beach. And we don't have a good understanding of how different the blooms are right in that 100, 200 meters from the beach. So we have the potential of doing that monitoring. We've just gotten this started. We hope by the fall we'll actually do into tests to be able to pull that in. And then we've also started respiratory forecasts as well. So all of this will ultimately come together so we know where the bloom is, where they're coming forward, and how to deploy the best job to keep people safe and to keep businesses in business. And that's the overall goal. Try to let people know what they're likely to experience and how to avoid the blooms. Thank you.
Thank you. All right. Last but not least, we have Dr. Alexander Gilerson.
Okay, good afternoon all. The talk is also new tools to monitor harmful algal blooms. And I first of all would like to acknowledge my collaborators. It's Dr. Sam Ahmed from City College of New York, Dr. Ahmed Habashi, who was a graduate
Excuse me, Alex?
at CCNY, now is in a
Could you speak up a little bit? You're a little bit faint.
Yes. Sure. And Dr. Rick Stumpf, who just presented on the similar topic, so you got information about Karenia brevis blooms in Florida, and you see another picture of the lifeguard who is in mask because of the Karenia brevis bloom, and he needs some protection obviously, and obviously the beach is closed. So a few words in introduction. Some things were already presented by Rick and previous speakers. But anyway, just to remind that phytoplankton are small particles in the ocean which absorb light and CO2, and through the process of photosynthesis produce oxygen. The amount is traced by satellite sensors on the global scale through concentration of the green pigment chlorophyll A, and increased value of this chlorophyll A is a proxy for algal bloom. Harmful algal blooms occur in various coastal areas in the U.S. and over the globe, and as a result of human activity and climate change, and affect fisheries, recreation, water quality, and need to be monitored, as Rick just explained. They can be monitored by measurements in the field, but it's efficient to do it through satellites. And there are currently two visible infrared imaging radiometer suite, abbreviation is WIRS, sensors on board of two US satellites. One is called SNPP, another is NOAA 20. And these satellite sensors have small number of bands, only 5 in the visible part of the spectrum is shown. And this is smaller than NASA MODIS, which was mentioned, and European Space Agency OLCI sensors, which are on Sentinel-3A and 3B. But these satellites still require tools for detection of algal blooms and their monitoring. Unfortunately, 2 bands in the blue for ocean color satellites, 412 and 443 nanometers, are usually strongly affected by uncertainties of the atmospheric correction, which is necessary to transfer signals measured at the top of atmosphere to water level. and because of that, they often are not reliable in coastal waters. So our project is aimed at the development of the reliable algorithm for HABS monitoring based on only three Wirtz bands, 486, 551, and 675 nanometers for the estimation of chlorophyll A concentration. So idea is that algorithm was developed using neural network approach or machine learning, where in synthetic data sets, absorption and scattering of the phytoplankton and mineral particles, which are primary elements in the water, and they were in various combinations were related to the strength of the light signal, which is called remote sensing reflectance, usually denoted as RRS, at these three bands, which I mentioned, 486, 551, and 671 nanometers. After training and testing of such data sets, they allow an accurate retrieval of chlorophyll A concentrations from measured RRS at these three bands. Performance of the algorithm is evaluated based on field measurements RRS of satellite RRS at these three bands in areas where chlorophyll concentrations were measured in situ. The algorithm was applied for the detection of HABs of Karenia brevis in the western Florida shelf, and also generally for the estimation of chlorophyll concentration in various coastal waters. Main findings: algorithm performs similar to the standard ocean color algorithms, which are based on 443, 486, and 551 nanometer bands in the open ocean and moderate coastal waters, and outperforms these algorithms in the near-shore areas, where atmospheric correction is especially difficult. For accurate evaluation of algorithms' performance, it is especially important to minimize time difference between in situ or satellite observations and chlorophyll measurements, as waters in bloom coastal areas have very complex composition and can change fast because of currents, tides, winds, etc. Algorithm efficiently detects Karenia brevis blooms at the western Florida shelf and can be used broadly for the estimation of chlorophyll, especially in coastal waters. Here are some demonstrations of our findings. You can see a global map of chlorophyll concentration determined using ocean color standard algorithms at the top, and using neural network chlorophyll algorithms at the bottom. In the broad coastal area, which is Gulf of Mexico, Area 1, colors are very, very similar, so there is no difference between performance of these algorithms. In another Area 2, which is Arabian Sea, colors are slightly different, which means that algorithms perform differently. We compared chlorophyll concentration retrieved using this algorithm for the Florida shelf Karenia brevis blooms, and that was done on the basis of the cell counts, which are characterize these blooms. And you can see here that correlation is quite good, at least reasonable, at the top layer for neural network algorithm, and becoming a little bit less accurate using other algorithms. And these results are shown for 100 minutes window, which means the difference between in situ measurements and satellite measurements. As we go to 15 minutes window, and meaning smaller difference time between satellite measurements and in situ measurements, algorithm performed much better, but neural network algorithm also performs better than other algorithms which are typically used in ocean color retrieval. Our group is part of NOAA, NASA, Navy validation team for ocean color satellites, specifically for this Wirtz sensor, and we participated already in several cruises on the NOAA ships. These are dedicated cruises in which multiple measurements are made, and specifically these remote sensing reflectances were measured together with chlorophyll concentrations, so we can use this data to evaluate performance of our algorithm for retrieval of chlorophyll concentration. Locations of these measurements at the East Coast are shown on the slide, as you can see, and on the left, the Florida, it's again locations of measurement of chlorophyll concentrations, where data are available from field measurements as well. Now we compare chlorophyll concentrations, which was measured in situ, in the cruises at the top, with chlorophyll retrievals using different algorithms. Again, neural network algorithms slightly outperform other algorithms, but not much, because they were not measurements very, very close to the coast. At the bottom, this is the case for retrievals for the Karenia brevis, and you see that neural network algorithm performs much better than other algorithms because we are very close to the coast, and that's the primary place where advantage of neural network algorithms can be seen. So to conclude, a new tool algorithm for accurate retrieval of chlorophyll concentration using WIRS data has been developed and successfully applied to the detection of HABs in West Florida Shelf and estimation of chlorophyll in various coastal waters. Why this is important? This algorithm will be used for earlier alerts of bloom conditions by coastal managers and for more accurate estimation of chlorophyll, which is used by fisheries in ecological models and characterization of in-water visibility. Algorithm is currently in the process for transition as operational, and as a next step, algorithm will be tested in application to other ocean color satellites to improve coverage of the areas of interest. There are a few references at the bottom if anybody will be interested, and we would like to thank our supporters. So this work is supported by GPSS Proving Ground project, and thank you very much for listening.
All right, thank you very much, Alex. All right, so next we're going to switch into the question and answer portion of this seminar. So if you have any questions, please type them into the chat box. Are there any questions around the room?
I have a question. Thank you, first of all, to all the speakers. Gary, I think my question is for you, and it's whether you have looked at or whether you would expect those areas of suitable habitat for the mussels to change with the projected changes in ocean conditions.
Thank you for that question. It actually is something we anticipated, and by altering depth, we think we can compensate in most areas for projected increases in temperature. As I mentioned, seasonally, the depth of the best conditions for mussels changes as it is, and so the expectation would be that the longline mussel aquaculture would allow farmers to adjust the depth in response not only to season but also to longer-term climate change.
And I have a follow-on question. How about interactions with protected species, mammals, seals? Are you concerned about that, Gary?
Yeah, that's the elephant in the room, of course, and we actually are in the middle of the process of hiring an ocean engineer to work very hard on that topic in collaboration with our regional office, with our science center expertise in protected species. But again, that wouldn't be worth the effort if we didn't beforehand determine that it was worth the effort of trying to address that one way or the other. And I'll mention something that some of the people in Maine, the fishermen interested in sea scallop aquaculture, are lobster fishers, and they're actually under a lot of scrutiny with respect to protected species interactions. And a lot of them are getting comfortable with technologies that avoid the use of lines, and maybe the long line model is not going to be the one that goes forward with mussels. But again, we've done the habitat suitability piece, and so again, knowing from the maps that Darian developed where we could put something that might not have vertical lines is possible still. We think there's a way around it. Let me put it that way.
Thank you. Rick, I have a question for you. Did you have a question? Go ahead. So I don't know if I understand the process really well of how, when you're offshore detecting HABs, you see all types of chlorophyll in, but then how do you, the ones offshore, how do you know they're Corinna brevis? Is somebody out there taking samples? And
in this particular case, there was a sample taken at one point, and so there was Corinna present. There was not all the chlorophyll based on our models, but it was, Corinna was definitely present at least in one place.
Okay.
Otherwise, there is a device, the name keeps changing. At one time it was called the Brev Buster, now it's the optical absorption meter, I can't remember the name. And there's a way to look at the full absorption spectra, and there's some distinct pigments for dinoflagellates that can be pulled out. That's not actually operating right now in those gliders, but it is possible. There's something out there would give a probability, that would indicate a higher probability that you're looking at.
Okay. And a follow-on question, I don't know if this is crazy, but can they put tracers on HABs? Has anybody tried to see if they, can you actually like coat something like a dinoflagellate or whatever with a tracer to, like, once you've identified it, to follow it actually? Some kind of fluorescent tracer or?
It has chlorophyll A in it. That's
yeah.
a pretty good.
No, but I mean, you can't
tracer.
distinguish that from all the other ones all the time, right?
Well, if you've identified, I mean, like the major blooms, I mean, even if you find something subsurface and you confirm it's Corinna, then if you can find it again subsurface, the satellite, it becomes very straightforward because you go through a sequence of images. And if you have a model, you can indicate where the bloom likely has gone. So even if you have a gap between data sets because the glider wasn't there or the satellite was cloudy, then you could use a model to move the bloom so you can recheck where it likely is. They don't appear in days and like suddenly grow and then die.
Right.
They're around for weeks at a time.
Right.
So there's not a problem of, oh, it's suddenly here and then it just disappeared. That does not happen.
And for all of us who aren't up on all the HAB monitoring that goes on in NOAA, can you just briefly tell us where NOAA is monitoring for HABs around the U.S.?
The Northeast, the Gulf of Mexico, the West Coast, and the Great Lakes.
Is there any up in Alaska?
We're trying to figure that out.
Okay. Thank you.
And all of them have significant HAB problems. Oh, Chesapeake Bay.
Are there any other questions on the line? Okay, do you want to?
All right, great. Well, a huge thank you to all of the speakers and also for Tracy for coordinating all these logistics. Let's see, so 2 weeks from now on March 4th, our third seminar in the NOAA Science Report Seminar Series will be a robust and effective research and development enterprise. This seminar will include lightning talks about predicting high weather impact events using water vapor information, using drones to map coastal elevations near shore depths, as well as to estimate harbor seal populations, and lastly, the Marine Biodiversity Observing Network. So we certainly hope you'll tune in for the third out of our 4 seminars. If you have any questions in the meantime, all of our contact information is available in the chat box. So feel free to reach out and share any questions you have. All right, well, thank you everyone. We appreciate your time and look forward to seeing you next time.
Great, thanks for joining us, everybody. Thanks especially to our speakers. Bye-bye.